Okay, guys, let's get started. We're talking about compile time computation. So we're definitely deep into compilers today. So if you raise your hand if you know Java. Okay, raise your hand if you know C++. Some people. Okay, cool. So we're going to spend the first half in Java, and then we're going to pivot to C++. But I'll be honest, I don't know C++ that well, so we're going to just talk about it on a kind of high level, superficial, because I can't get into too much detail. I'm a fan of Python and Java. So yeah, Java, we're going to talk a little bit about static analysis, and then we're going to pivot into C++. So, okay. Compilers, I said on the first day, are a great example of metaprograms, right? Because what's a compiler? A compiler is a translator. It takes in a program, and it translates it to some other language. So, most compilers translate a high-level language into a low-level language. And so an example would be the Java compiler. The Java compiler translates Java code into Java bytecode. And then the Java bytecode is then interpreted by the JVM. So Java is a compiled language in that sense. Another example is Clang. If you've done 2150, I'm sure you've called Clang. Clang is a compiler that compiles C++, or actually Clang compiles C into native bytecode. So, but it doesn't have to be that way. Basically, compilers just translate languages in general. So a lot of compilers translate to some intermediary representation. So there are compilers that compile to assembly. Or, for example, there are compilers that compile Python into C, that kind of thing. So you can think of compilers as just translators, and they treat a program as their data, and their output is a different program that does the same thing, but in a different language. And we usually think about the compilation pipeline kind of like this. We've got a program in some high-level language, that's Python up there, very high level, and it gets compiled, and then it gets compiled some more until eventually we get some binary representation that the computer is able to understand. Now, there's a little bit more to this, because here we're writing a program, and our intention usually is for this program to be translated. We write the program knowing that the compiler will turn it into a different program. And because we know that, sometimes we get to speak to the compiler directly. So there's actually this kind of more roundabout way of programming, in where you write a program that gets translated, but you also tell the compiler how to translate it partially. And that's what we're going to be talking about today, compile time computation. It's a whole subset of metaprogramming, and it's a lot of people really like it because you can use it to do really fast things. You can cut down on code reuse, or you can, increase code reuse, and you can make things faster. Okay, so when we talked about Java the other week, we talked about annotations. Here's an example of using an annotation. You say @ and then the name of the annotation. You can pass some values in, and you say the annotation right before the thing that you're annotating. So one annotation that you guys have probably all used is @override. You say that before methods. But you can actually put annotations anywhere. You can put them before fields. You can put them before classes. Actually, there's a couple of scenarios where you can't, but you can put them many different places. And what they do is they just add metadata. They mark this construct in some way, but they don't change it. This isn't like Python. In Python, we use the exact same syntax for decorators. And decorators had complete control over what they were decorating. A decorator in Python could completely change the behavior of this function. That's not annotations in Java. In Java, the annotation is just assigning metadata. And just, again, this is a short review, but you can write your own annotations with some meta annotations. These are annotations that are going to mark our annotation. So this is how you define an annotation. This was the annotation we used before. And this says when the annotation is defined. So this annotation is going to be relevant at runtime, and it's going to be used for annotating methods. That's what that means. And then you can define the data that you're going to store. This is the metadata. So there's actually two levels of metadata here. There's the fact, if we use this annotation, the fact that that thing is annotated with this annotation is metadata. So like if you say at test, you don't have to pass any parameters in. Just the fact that you said at test means that method is a test method. So that's metadata. But then you can pass additional metadata into your annotation. So does everybody understand what I mean by metadata? It's data that is stored about something, but isn't that thing in and of itself. So some metadata in the context of files would be time created, or file type, that kind of thing. That's metadata. So if annotations only create metadata, then they don't actually do anything, right? They just kind of exist. So they're pretty useless, right? Well, no, of course not. No, they're useful. The problem is we just have to create meta tools to use that metadata. And we call those meta tools annotation processors because they process the annotations. And this is compile time computation because these annotation processors are called by the compiler when you compile your code. So an annotation processor is just a class that extends the abstract processor, and it implements the process method. And then the process method takes in a set of annotations and the environment that was defined by the file which we're processing. So for my annotation, which we saw earlier, there might be some corresponding annotation processor that we would write also, called my annotation processor. And that would take in a set of everything annotated and then the rest of the file also. And what the method can do, well, it can't change the file or definitions. Like we said, this isn't like Python. We don't have that kind of power. But we can have side effects. So we can throw an error. That's what at override does, right? If you say at override, but you're not actually overriding anything, you get an error. So that's a side effect. That's a side effect of the annotation that isn't changing the behavior of the code. It's just causing a side effect at compile time. And you can do other things. You can generate code. You can do that with Java Poet. So that's why I talked about Java Poet last week, is because if you happen to want to write an annotation processor, this is really useful. It allows you to make really dynamic code, but we'll get into that. So I've mentioned it at test. That's an annotation. Turns out JUnit is basically just an annotation processor. JUnit is connected to your compiler. There's a complicated method of registering annotation processors with your compiler. I'll be honest, it's a hassle, and I honestly I could not get it to work. So I wanted to give you a demo of this, but Eclipse just was not working with me. So I'm going to talk about it briefly, but yeah, JUnit is basically just an annotation processor that's associated with the compiler. And what it does is it looks for methods annotated with at test, and then it causes some side effects. Those side effects are it runs the method in the testing environment, and then it displays the result. Override checking. It's another instance of an annotation processor. But in this case, the annotation processor is the compiler. You can think of compilers as yet another annotation processor, because it also has the power to look for annotations and cause side effects. So here, it searches for methods with, that's a typo. That should say at override. Override checking searches for at override, and then it causes some side effects. It'll check if the method actually overrides, and it'll throw a compilation error if it doesn't.
So is it required to do at override if you're overriding method?
No, it's not required. So yeah, this is just metadata. It doesn't change anything about the behavior of the code. If it's valid code before, it's going to be valid code, after whether you use the annotation or not. What it does do, though, is signal to some processor somewhere that we want to do some meta processing on this. And so in this case, for at override, the meta processing is just an extra check. Yeah. Here's another example. This one is not built in. So JUnit you can get with Eclipse. At override is built into the compiler. But this is just a cool one I found, built by some Google engineer a couple of years ago, called Kofoja. I'm not sure if that's how you pronounce it, but it implements contract-based design by contract for Python. Design by contract is when you design your code base with where every module fulfills some contract, and you write that contract first, and then you write the methods that fulfill that contract. So you could say, like, we've got this class, and it takes maybe this is a pizza shop class, and it takes in a pizza factory and a building. Part of the contract for your pizza shop class could be, well, we're going to require that the building has at least 1,000 square feet. Something like that. Just any sort of requirement for your module to work is part of the contract. And you can also think of this as preconditions and postconditions and state requirements. So this is a way of implementing that. The way it works is it looks for these annotations. And if you go, this is open source, which is why I mention it, because you can go into the GitHub repo and look at the definitions of these three annotations. And you can also see the annotation processor class. And you can see it searches for these annotations, and then it causes some side effects. The side effects are that it generates code that does the same thing as the original code, but inserts some checks. And it checks the pre and post conditions at runtime. So what this basically allows us to do is have two versions of the program: the safe version and the unsafe version. So this framework automatically copies your code and creates a safe version that inserts a bunch of checks everywhere for you. So I said here, side effects, generates code, may throw an error if the conditions don't compile. That's kind of weird because we're talking about an annotation processor here. This is external of the compiler. Well, it turns out that this annotation processor takes in some strings as metadata, and then it uses the Java compiler to compile those strings. So this is an annotation processor that's registered to a compiler, but is also using the compiler itself to build the data that it needs to do its thing. This means that you can get into really weird stuff because these conditions here, the preconditions, postconditions, can actually be Turing complete because it can be any Java program. So you could get into scenarios where you say, run this method if and only if Fermat's last theorem is true, and that would never execute because no program can ever solve that problem, or something. It's unsolved or something. Take theory of computation if you're more interested. So I want to show you an example of this Kofoja library because it's really cool. And like I said, it's all open source. This is an example of its usage. So see, we've got @requires and then some strings, some requirements, and the strings say the current buffer should be not null, the tokenizer shouldn't be null, and the token can't be null. So that's a contract for this method, transform common, which takes in those things as parameters and then does some stuff. So you can see it takes in these three things. How did the annotation processor know what token is? Well, because it compiled that string in the context of this code. So that's very meta. And there's one more meta thing going on here. Can anyone guess where I got this function? Yeah?
Presumably from Kofoja itself.
Yeah. This function is part of the Kofoja library, which means that the library uses its own annotations to design by contract itself. So very meta, very meta. And you can actually see this in all sorts of things. Like Java Poet is not an example of this, but you could write a version of the Java Poet library that was built by Java Poet. And that unlocks all sorts of really cool meta things, and that's what we'll be talking about next lecture after Thanksgiving break. Okay, Any questions about annotation processors in Java? Because we're about to pivot. No? Okay. I know that wasn't in a ton of detail, but like I said, it's really confusing to actually get Eclipse to do it. So if you want to try it out, good luck. Okay, static analysis. Who's heard of static analysis? A couple people. Okay, cool. Yeah, you're a Mechie? So yeah, not that kind of static analysis. Although there's also dynamic analysis, but this isn't dynamics. So, static analysis is a method of code checking where you write a program that checks the correctness of the program that you're interested in without running it. If you were running it, that would be dynamic analysis. And a classic example of dynamic analysis, I'm not sure if this qualifies, but unit tests, that's kind of dynamic analysis because you run the code and you check that it works. Here we're not running the code. We're trying to see if it works without running it. That's static analysis. This problem is intractable or maybe not even solvable. But what we can do is give our best shot. We can, if we accept some false positives and some false negatives, we can do an actually pretty decent job of writing code that analyzes other code for correctness. And the way we do this is usually by extending an existing compiler, because it's awfully hard to check the correctness of a program without understanding its structure in some way. If we were writing a static analyzer, but our input to the static analyzer was just a string, the string of the program, the file, that would be really hard because you would have to write all sorts of code that understands that parentheses should match and ignore comments and classes are not the same as functions. You'd have to write all of that. But the thing is, that's already all been written for you by the compiler. The compiler already understands all of those things. It knows that parentheses should match, that functions are not classes, that there's a certain amount of nesting that goes on when you write a program. Because the compiler already understands that, what we do is we extend the compiler. We add some hook or handle onto the module, onto the compiler, and then the compiler will do these things for us. And some of the extra checking you can do is you can check convention. That's a linter. So who's heard of linters? Yeah, so a linter is just a module that you can add to some project, and it'll check your code conventions for you. And it'll throw errors if you don't follow code conventions. That's a static analyzer. And we can also check for correctness. That would be a program prover, or there are different variations of that. I can't get into any more detail about how these things actually work because it's dependent on how the compiler works. And so if you're interested in this more, I highly recommend you take Theory of Comp, compilers, and then sometimes there's a special topics class on static analysis. So yeah, it's cool stuff, but I'm not prepared to talk about it anymore. So just be aware that it exists, and this is definitely an example of metaprogramming because you're writing a program that checks another program. Okay, C++. Like I said, this is not my language, so correct me if I'm wrong on anything, James. James is really good at C++. Okay, so macros. Macros are the quintessential C++ metaprogramming feature. Who's written a C++ macro? A couple people. If you're in 2150, I think you probably have written one, right? Because you always start your function by saying, if not def this. And then, right? Isn't that how you, yeah?
Yes, I guess so, yeah.
That's how you prevent import collisions in C++. That's macros. Every time you say hashtag define or hashtag ifdef, that's all macros. And they're definitely metaprogramming. And why are they metaprogramming? Because you're really writing two programs at that point. If you use macros, you're writing two programs. You're writing your C++ program, and then you're writing your macro program that tells the C++ compiler how to translate your C++ program. I mean, that's meta. That's so meta. Macros are pretty cool. They if you use them in a structured way, they let you solve some really annoying problems like import collisions. And they can also speed up your program because every time you write a macro that computes something non-trivial, that computation is going to be happening at compile time. And so you can save yourself some computation if you put some logic in the macro instead of in the function. But, yeah, okay, I'll get to it. Yeah. So here's a definition, here's a macro. Pound define, maxint, and then that's the maxint in C++. And we've got a main function. We're going to print the maxint. Oh, and I already see an error. I told you, I left out the semicolon. Yeah, I'm a Python guy. But, okay, what do you think will happen? Yep, prints the number, yeah. And so at this point, it looks like macros are basically just variables, right? So we just defined a variable maxint, and we're printing out that variable, right? Yeah. Okay, you can also define functions, function macros. So this is a function macro. It takes in an n, and it evaluates to whether or not n is equal to the maxint. Now, if we print out max of that number, I believe that prints true, I think. Okay, these are the simple examples. Let's define this square macro. It takes in an x, and it multiplies it by itself, right? And we print square of 1 plus 1. What gets printed? Who says 4? Who says not 4? It's not 4. This prints 3. Wait, what? That's a typo. It prints 3. What? Darn it.
Sequence.
Oh, what? I lost the bombshell. All right. This does print 3. Does anybody want to explain why?
So this is just straight up textual substitution, not lexical substitution.
Yep.
So it would be 1 plus 1 times 1 plus 1.
Yep. Macros are dumb. They are stupid. They are so... This is bad. This is so bad. Because macros literally do text substitution. They look for the square function, and if they encounter that, they replace whatever we put in the middle there by x in that expression, which means that this actually evaluates to 1 plus 1 times 1 plus 1, which is 3. Does that make sense? So, yeah, macros are stupid. Why is this not what we expect? Well, because usually when we call a function, we expect the parameters to be evaluated first. If square were a normal function, then the compiler would know, okay, there's a certain order we have to do things in. You first must add those two parameters, then you can pass it into the function. Macros aren't that way. They are not regular functions. They are text substitution tools. And so when we do square x equals square, x times x, it literally substitutes that text in for x. So we could fix this in a couple ways. This is one. Now we're going to say, do the text substitution, but just put everything in parentheses to make sure that we don't get any, so make sure we follow PEMDAS. What is this going to print? Yep. Segfault?
Because printf takes in a string as its first argument.
Okay. So I told you I hate C++. So pretend this is a C out. What? Okay. Ignore the fact that I'm printing anything at all. Just what does this evaluate to? What does this evaluate to? Four? Who says 4? Who says 5? Who says 6? No one says 6.
I'll say it.
Okay. Remember that macros just do text substitution. So if you take the square of plus plus x, that's going to evaluate to plus plus x times plus plus x. Do you see how this increments x and then puts it here? So at this moment, we've got what's x? 1. This is 2 times, now what's x? 2. And so we increment it again, and we get 3. That should be times. So you could argue that it's 6, right? So is it 6? Or is it 4? It's actually undefined. You have no idea what the compiler is going to do. It depends on the compiler. It depends on the system you're on. It's undefined because it's illegal to modify a variable like this in a single line. It is an undefined behavior. You can't do that. You cannot call plus plus x on the same line twice. So sometimes it'll be 2 and sometimes it'll be 3. I mean, sometimes it'll be 4, sometimes it'll be 6. All right? Are you convinced that macros are bad yet?
You may be very grateful for Python.
Yeah. Okay, let's check out this macro. I love this one. Who's heard of the ReLU filter? Okay, a couple. Okay. The ReLU filter, if you were to graph it, looks like this. It's a function where you put in a variable, you put in an integral, a number. You put in the number, and if it's negative, it just bumps it up to 0. Otherwise, you get the number. It's a filter that's applicable in machine learning. Machine learning uses this filter as an activation function in networks, neural networks. But you can think of it as just a function that takes all negative numbers and turns them into 0. That's it. That's the function. And that's what we've implemented here in this macro. We say every time we want to take the ReLU of x, if the x is negative, make it 0. That's it. Super simple. That's it. All right. Let's take this program. Got x is negative 1. If true, ReLU x, else unreachable. Because, this is unreachable. We've got an else here, but the if was true. So, if this even compiles, it's certainly unreachable. Because you could never get there. Again, ignore my usage of printf. I did not know that the first parameter has to be a string. So what gets printed? I just flashed it. All right, it's 0. Because negative 1 is negative. If true, ReLU of x, well, x is less than 0. So we assign x to be 0, and then we print it. How about this one? What gets printed? Unreachable 1. Yep. Because else statements always pair with their nearest if. Right? And this just does text substitution. And so this macro substitutes this for an if statement with no else, which means that this else is going to associate with that if statement, which means here we got lucky. Here this didn't print because the if was evaluated. But if the condition is false, that if statement will be false, and the else will evaluate. So we would get this unreachable code that actually does reach. All right, and now are you convinced that macros are bad? Yeah? Okay. All right, let's check out this one. This is the last one. We've got a macro, it takes the max of A and B. And then this is a ternary. Who knows ternary? A couple people. What this says is, if A is greater than B, evaluate to A, otherwise evaluate to B. It's an inline if statement. And we're going to include algorithm, and we're going to have some code that calls sort. Will this work? Who says it will work? Who says it won't work? This won't work. Because we've defined this macro, max, and then we're importing algorithm. Algorithm has a function called max. And macros don't have a namespace, which means that we would have a name collision, and I'm pretty sure this won't compile. Because the moment you say pound include algorithm, and we've got weird things would happen. It certainly wouldn't behave how you expect. And I'm pretty sure it wouldn't compile at all. So macros have no namespace.
So So I think what would happen is it would import or it would include algorithm, and then the function definition for marks would then be, the name would be overridden by that ternary expression. So it certainly
Yeah.
would compile.
So it would compile?
It certainly would not.
Yeah, it wouldn't compile, right? Yeah. Yeah, it would. This wouldn't. There's no way this compiles for several reasons. Yeah. So yet another reason that macros are bad. Not to mention, you can't debug them because they immediately get preprocessed into new code that you didn't write. So all of a sudden, all of your line numbers are off if you have a macro that's multiple lines. So they're just bad, and they're ugly too. So we want to avoid macros. So there's this alternative thing. Remember, one of the reasons we wanted to use macros was to get a speed up. We could compute certain things at compile time instead of runtime, and that would maybe save us some time. We can do the same thing with const and const expert. What these do is, they basically mean final. They mean this thing cannot be changed. And if something's not going to change at runtime, what does that mean? It means the compiler can compute it at compile time. If it's not going to change, then we don't need to compute it at runtime. So const and const expr can be used to get many of the same speedups as macros. And in fact, in C++ 17, they're expanding, or 17, 18, 20, I'm not sure, but they're expanding const expr to be even more powerful. So now you can use const expr if, which does compile time branching. So you can do a lot with this. You could write entire programs that are const and const expr, and they would all be compiled at compile time, and then the result of running the program would always be constant time. So yeah, interesting stuff. And what they allow you to do is you can adapt to your compile time environment. So let's say you're a library writer, and you're writing some functions that you're intending for other programmers to use, or some classes, some structs, whatever. If you use const expr, let's say you use a const expr if, that's a compile time branch. And what that will allow you to do is change what gets compiled by your library at compile time. And so what you can do is you can check certain things, like did the programmer who's using this library actually use this class? If not, you could replace it with a dummy class, and that way all of your dependencies stay in check, but you don't actually spend the time compiling, and you don't take up the code space. That's something you could do with const expr if. So really cool dynamic compile time computation. Questions? Okay. All right, there's one last form of compile time computation metaprogramming. It's templates. Templates are usually used for generic programming. So this is an example of a templated function in C++. It takes in two things, an A and a B, but the types of those two things are determined by this type parameter, T. And what this allows us to do is avoid rewriting this function multiple times. What the compiler is going to do, actually, is it's going to check for every time you call this function, it's going to check, okay, what type did you pass in here? And then it's going to actually copy this function, but inserting that type for T. It's actually going to create a new version of this function for every usage with a new type parameter. And that's all going to happen at compile time, which means that we have a bit of a hook into the compile time here. So what you can do with templates is pretty cool. Here we've got an add function that takes in x and y, and it returns the sum of x and y. This happens at runtime, right? So if we call add in our program, at runtime, it's going to add those two numbers, and it depends on what they are at runtime, and the addition will occur when you're running the program. It's going to increase the time it takes to run your program. It's all happening when you run. We can write the same thing, but it'll happen at compile time, and this is how. We make a template, and most of the time when you write templates in C++, if you're using them for generic programming, you take in type names, take in type defs. But you can take in anything you want, actually. And so here, we're going to write a template that takes in an int and an int. And then we're going to define a struct called adder. And this struct is going to have an enum. An enum is basically just a name to value pairing, if I understand correctly. So this is just going to associate the result name with this value. But the trick is enums get computed at compile time because, they're const. So if accessing the result variable will return the same value every time because this is const. Because it's const, it's going to be computed at compile time. And you could use this just like this. Again, I'm so sorry about the printf thing. I've been writing too much other stuff, so I haven't written in C++ since 2150. So, okay, you're printing adder, and then you pass in as template parameters the two things that you want to add, and then you access the result name. This will compute at compile time, and so at runtime, this expression is essentially 7. It's 7 because the addition was computed at compile time. The compiler is going to look at this code and it's going to say, oh, we're using the adder struct with some new parameters. So we better make a new version of this adder struct for these parameters. And what's the result? Well, we better compute that result so it's accessible at runtime. And the result is 7. And that's all going to happen before the program is even outputted by the compiler. Pretty cool, right? Turns out, templates in C++ are Turing complete. You can write any program with only templates in C++. You can make the compiler do arbitrary amounts of work by using templates in this horribly abusive way. So here we've got a factorial function. It's recursive. This is another ternary. If n is 0, return 1. Otherwise, return n times factorial of n minus 1. Factorial function, classic. Here is a compile time factorial function. This will compute factorials at compile time. You'll be making the compiler compute factorials for you so that they're not computed at runtime. We've got a struct that takes in an n. The struct is called factorial. We've got one value. The value is equal to n times the factorial of n minus 1, : value. So this is a recursive struct definition that's compiled recursively. And then what you can do in C++ is you can do type specialization for templates. You can say, use this generic template form for any n, unless we get a certain n here, 0, and then use this form. Question?
It can be like, but wouldn't it go down to negative?
Yep. There's no apparent base case here, but what you can use is basically the built-in. There's a sense of template overloading in C++, and so we're basically overloading the template here such that when it's called on 0, we use this form, and then this form, of course, will just be value equals 1. And this works. You can compute factorials. You can force your compiler to compute your factorial at compile time instead of runtime. And obviously, before the before case was pretty trivial because adding is extremely fast. But calculating factorials can get kind of slow. So if you need the value of factorial of a 70, that's a huge number. And you don't want to be computing that at runtime whenever you need it. You want the constant. So one way you could do that is you could just hard code the constant into your program. But you know that's bad because I used the word hard coding. What if you got it wrong? Or what if you want to change it from 70 to 71? You'd have to remember to change the value there. It's all sorts of dangerous things can happen when you're hard coding. So this is much better. What you say is, we want the constant factorial of 70. But we don't want to hard code it. We want the compiler to figure that out before the program runs and turn it into a constant at compile time. And that's what this does. So this saves a non-trivial amount of time. And yeah, that's it for today. That's compile time computation. Yeah, I wish I could have gone into more depth, but again, I'm not a big compiled language guy, so it's about the best I can do. Next week we're going to pivot to Lisp/Python kind of hybrid. We're going to talk about homoiconicity, and then that's going to be the real last content lecture. The last lecture is going to be pretty fun. We'll just do a recap. I'll talk about some things that I skipped, and I'll bring in Bodos, and maybe we'll do the final exam, or maybe it'll be take home. Not sure. So yeah, we've got 8 minutes left. I'm not going to hold you, but I recommend that you find your teammates from last class. And if you weren't here last class, I recommend that you try to join a team. And this is for the last homework. The last homework is due on the last lecture. It's the Java homework, and it's a team homework. So you can do it by yourself if you want, but it might be more fun if you do it as a team. So if you weren't here, try to join a team. Just check in, and yeah, that's it. Have fun.
Yeah, but